Welcome, everyone. It's great to have you here. It's great to see so many of you back. A lot of you have attended all the previous webinars in this GX intro series. Today we are going to finish it off with a technical session on foundation. And Christian will guide you along how you do that in OPTUM GX. And as always, I think he will do a great job at explaining. Next year we will host other sessions, and if you have any wishes for what topics you would want us to cover, feel free to send them directly to me or to Christian afterwards, and we can take that into consideration when we plan for the next year. And as always, I will send a link with the direct link to rewatch this episode of or other sessions we had in this series. And feel free to ask any questions in the chat as we go. I think Christian will pick up on them at the end of the webinar. And I will hand it over to you, Christian.
Thank you, Isabella. Yes, I think what was meant by this title, foundations, was shallow foundations. So I think one of the first things we'll do next year is have a webinar on deep foundations, piles. But today it's shallow foundations. So that's of course a huge area. Geotechnical engineering is also sometimes called foundation engineering, and so it's a very large area. And I'm really just here to give some guidance on how to set up models and conduct analysis in GX. I have some topics that I wanted to just say a few things about. They're shown here, and then I will sort of illustrate by example. So it's first of all bearing capacity of foundations, objectives of general loading. Then there's something on interfaces that I think I would like to say a few words about. Embedment is also something that is not really particular to GX, but I think something that is worth being mindful of, how it's handled in FE, or how it can be handled in FE, and how it's handled in the codes of practice. Then 2D versus 3D settlements, and finally something on generation of VH diagrams, or actually VHM diagrams for sort of foundation subjected to combined loading. But I can't really get started without mentioning Tasaki's bearing capacity equation, at least not on the topic of bearing capacity. So of course that's been around for a long time, and it's very widely used. So there's three terms. So the ultimate limit load is the sum of these three terms, something related to the cohesion, to surcharge, and to...
Sorry to interrupt, Christian, but I don't think you're sharing the screen.
Oh, well, it says I'm sharing.
Oh, maybe you are. My mistake.
Okay. Can you see it?
I see it. If there is if anyone doesn't see it, you can write in the chat and we can fix that. But I see it now.
Yeah, good. And a term related to unit weight, and there's the bearing capacity factors, NC and Q and gamma. So this equation here, well, it comes with some assumptions, small deformations, so no changes in geometry up to the point of failure. That's sometimes it's usually not too bad of an approximation. Sometimes it's not too great. If you have a foundation that you really press into the ground, then of course you generate surcharge, you generate a Q term, you generate some embedment, so that changes the bearing capacity. And if you reach that new capacity, well, you generate more embedment and so on. So it is a simplification that sometimes holds, sometimes not so much. Associated flow rule, that's something that's been talked a lot about. That's of course not realistic that we have as much dilation as friction, but it has not too huge an impact actually at the end of the day, especially not compared to the first one here, and also various other effects. More Coulomb perfect plasticity. I would say in 2D it's kind of okay. It's not that great in 3D. We know that the friction angle depends on the stress state, so it'll be different in, say, triaxial compression than in triaxial extension or plane strain. There's also something with this with the stress level. So the friction angle tends to increase as the stress level decreases. That's of course not accounted for by more Coulomb. Superposition, so that's the idea that you can add these three terms, and it's well known that you can't do that. It's also well known it's conservative to do so. And then there is the bearing capacity factors, and I just wanted to mention this, NC and Q and N gamma. So the exact expressions for NC and NQ have been available for a very long time, I think since the 1920s. Prandtl and Reisner, I believe, were the ones who came up with them. Closed form solutions, and they're universally recognized. No one uses anything else. Then there is N gamma, and the exact N gamma is actually also available. It hasn't been available for 100 years, but it's been available for 20 years. Since 2005, Chris Martin came up with basically a methodology to calculate N gamma with a pretty much arbitrary degree of accuracy. He didn't come up with a closed form solution. I don't think that's really possible, but he came up with the next best, and that's numerical solutions that are very accurate. I think 6 digits or something like that. And so it's in a paper here. I downloaded it actually from Google Scholar this morning. 20 years old, and with the exact N gamma. But for some reason that's sort of not been recognized as exact. I don't know why. It's not in the codes, it's not in the textbooks, it's sort of not really been recognized. I think it should be on the same level as NC and NQ. But since 20 years have now passed, I wouldn't hold my breath. But nevertheless, it is exact. And if you run N gamma problems with GX with enough elements, that is the N gamma you will reproduce, not some random N gamma from the code or from some textbook. It is the exact N gamma. Of course, you'll reproduce just as you'll reproduce the exact NC and NQ. So that's how that is. So that's the paper here. Tabulated values of N gamma. A very good fit is this one here. I like this one a lot because it is kind of very similar to Meyerhoff's N gamma. There's the factor of 1.4. If you reduce that to 1.34, you get a very good fit to the exact N gammas. And in any case, it's definitely much better than the one that is currently in use in Eurocode 7. I hear it's going to be updated to something that's a little less wrong, but I think it would make sense to just update it to the exact. But as I said, don't hold your breath. So that was that, and then let's switch to GX. And I was going to just set up a very basic example just to get started, and that's the one shown here. So foundations is one of the easiest problems actually to handle in GX, one of the most straightforward problems to handle. And it can be done sort of, there's two variants of it. In both variants, you start with a soil domain, and then you can draw a foundation that you can then model as a rigid solid. So we have some embedment here as well, and then let's say we have a more Coulomb material, and I will say it's 0, 30, 0 cohesion, 30 degrees friction angle, and then 18 kilonewton per cubic meter unit weight. And the foundation, we can just use a rigid. That's the usual sort of infinitely strong, infinitely stiff material. Let's just keep the unit weight at 0. And then we want to know, if we apply a surface load like this, what is the bearing capacity we need to support this with standard fixities is usually the way to go. And now we're set up basically to determine the bearing capacity, and that is the analysis type known as load multiplier. And you then press run, and you get a bearing capacity 822 kPa in this case. So 822 times the load that we have on, which is 1. So, and we have the mesh settings here. We could increase the number of elements, as I think I've kind of covered in other webinars. With the mixed element here, it's very accurate even for small numbers of elements. So yeah, and you can see that here, 822 to 810, let's say. That's not a huge change. And it's also possible to use, of course, mesh adaptivity. And where you adapt the mesh, you solve once for a sort of a more or less uniform mesh, then adapt the mesh in a couple of iterations to end up with a mesh that looks like this. And if we plot collapse mechanism, it looks like this. And then the first problem there with actually that I mentioned on the list is this issue with embedment, because the way the codes, at least Eurocode 7, and I think most other codes, is kind of the way Tasaki's bearing capacity equation works as well, is that you always make reference to the base of the foundation. And then you might have some soil here next to the foundation, and you kind of assume that the weight of this acts here, but you have no effect of the strength of this soil. So actually a model that sort of looks like this, where we would have a fixed load here, and that would be 18 kPa, because 18 kilonewtons per cubic meter times 1 meter embedment. And we then get in this case, not a huge difference, 723 versus with embedment 815. So yeah, not orders of magnitude, but it can be. There are examples, especially for clay. So when we do sort of undrained analysis, usually use the Tresca model, and I have an example of that here, where it can really be quite severe. So this is an example of a foundation on a Tresca soil with 1 meter embedment, and I start here with the now I have a unit weight here of 10, so the embedment corresponding to 1 meter is 10 kPa, and then and then, oh yeah, that's been done in a little bit the wrong way. Let's do it the right way. So we shouldn't, of course, have, it should be, yeah. So let's say that we have this model here. This is our actual physical model. And then we have sort of an approximate model where we take the surcharge into account, but where we have no soil up here above the base of the foundation. And this is a circular foundation. You can see I've turned on axis symmetry. So let's see what happens. And what happens is that let's say the correct problem, or physically maybe correct problem, if you can trust this soil up here, you have a capacity of 1074, and then the approximate one, where you only include the weight of the soil, it drops to 619. So almost a factor of 2 in this case, and that's of course because the soil has to kind of, in order to fail, it has to fail up through this soil here. And if we plot the strains, maybe to have a look at the failure mechanism, something like that, There's some strength here, and of course here as well. The interfaces need to be considered here as well. I'll cover that in a second, as opposed to here where there's no resistance in this air up here. So it can make quite a difference. How exactly you choose to model things, and I had an example here as well where there was something in between where I have 100 kPa on-range shear strength down here, and then I've reduced it by a factor of 2 up here, and yeah, well then I get a capacity. I shouldn't have had this one here. I don't know what happened here. Then I have a capacity that's somewhere in between the two extremes, of course. 870, which is in between 1074 and 619. So that's how that is. Let me just go here. Yeah. So I said there was two ways of modeling foundations. One where you actually model an actual foundation, a rigid block, a concrete block. And the other possibility, which is also sometimes often useful, is to use a rigid plate instead. If you have surface foundations, for sure, that's the way to go. But even if you have like a block, it may be useful to actually apply a rigid plate element. And the reason for that is that if we have plate elements, so let me just draw, if we have solids, just delete all of this. So this is one version of it, and I have a rigid. So to solids, only surface loads apply, so kilonewton per meter squared. Because if we start applying not point load, but concentrated loads, line loads like this, then we have a stress singularity, and we eventually get to a limit load of 0. That's how it is. So if you work with solids, this is the surface load here is the only sort of real load you have at your disposal, which is not always very convenient, especially if you have some moment loading as well. So for that reason, it might be a good idea, if you really want to have the solid, to just simply apply a rigid plate on top of the rigid solid, and then you can to this corner, to this node here, the central node, you can then apply line loads, kilonewton per meter line loads extending into the plane. And that's what I did with this foundation here. So it's a surface foundation on a Tresca material, on clay undrained. It has an undrained shear strength of 50 kPa. And it's 2 meters wide, and this is in plane strain. So the solution should be the famous the width 2 meters times 2 plus pi, 5.14 times 50. So that's 100 times pi. And for this mesh, well, I get something that is very, very close to that, and the classical mechanism as well, which in this case looks really quite nice. Maybe somewhat surprising, because there is a tendency, yeah, you can see it here as well, that there will always be some asymmetry in the mesh. So even though the problem is fully symmetric, well, there's a tendency to either rotation or sort of a non-vertical movement of the foundation. But in this case, the slip lines look really quite nice. Rotational mechanism is also equally valid, of course. So, and then you can also, in this case, start playing with the eccentricity. In the case where you have the possibility to apply a line load at a point, you can start playing with it. Yeah, first of all, you can, let me show you how it works. So here I have a single load, because this is a little bit different from G2. I have a single load where you have various options. Is it multiply or fixed? There's something with coordinate system. The load direction, so that's in the y direction, and then the magnitude. If you want a horizontal load on top, well, then you need to add another load like that. So let's say we had the horizontal load and it was 1/10 of the vertical load. And then that should work in the x direction. And then unfortunately you can hardly see it, but there is a little horizontal arrow there. And then we can try to solve that. And that of course has quite an effect. So then we sort of slide like that. And also you can start very easily if you have eccentricity, as in this case here. Have both a horizontal and a vertical load, and there's an eccentricity as well. So effectively a moment with reference to the center of the foundation. What you see is that things begin to lift off like that. They begin to lift off if you have the right interface conditions. And that brings me to that whole business with interfaces. So in G2, in GX, the same in G2. GX, it's a little bit more convenient, but so when you have a plate element, they automatically come with interfaces. And the default settings are actually the ones shown here. So material adjacent solid means it takes the interface material from the adjacent solid. In this case, it's a Tresca, but you could change it to whatever you want. If you want something else, then you can do that. It's usually not relevant. Usually it's the parent soil material you want. And then there's a reduction factor. So that applies to C and phi. In the case of Tresca, it's to CU. So that's 1. That could be anything between 0 and 1. And then there is a possibility of having a tension cutoff as well. And the default setting here is yes. So there is a tension cutoff. And that is basically what brings about this lift off here, right? So you otherwise, without a tension cutoff, you would have something, we can try to see. So tension cutoff, no. You would have something where the soil would stick to the foundation. So it would sort of look like that, which is not really usually not realistic. You would think this would be more along the lines of what you would expect with a high eccentricity. So that's taken care of, so to speak, automatically. If you don't do anything, you get a tension cutoff and you get a reduction factor of 1, so meaning no reduction of the strength at the interface, same as the soil strength. Sometimes you might want to reduce that. You can do that here. But what do we mean by a tension cutoff? Because I've become aware that there's different takes on what a tension cutoff actually means. We wrote a paper about it. Let me just make a small advertisement for that some years ago. Myself and my colleagues here in OPTUM. I believe there's one right way of doing it, but there is another way that is also widely used that is a little bit, maybe from a numerical point of view, it's convenient, but it is not really what I would consider a real tension cutoff. So if we use a Tresca, so for undrained analysis in sigma tau space, this failure criterion looks like this. We have Cu, so the maximum shear strength, shear stress is Cu. And one way of limiting tension is to cut off to make a cutoff like this. So in this diagram, it sort of seems to sort of be correct, but it's not really completely fully good, because if you look at the point up here, so a point of pure shear, Well, so full CU and no normal stress. Well, what you have then is a situation like this, but that is a situation that is equivalent to this one here. So equal tension and compression under 45 degrees, equal to the shear stress CU in this case. So actually you do have tension in a so-called tension cutoff like this. And what you really should do is you should look at a Moore circle and then place a Moore circle so that the smallest principal stress is always positive. And then you get an effective yield criterion, failure criterion at the interface that looks like this. So a semicircle and then the Tresca. Or if you apply some kind of reduction, well, you get the purple one here instead. That's the way tension cutoff is implemented in GX, and I believe this is what is meant by a tension cutoff. There can be no tension in the interface, neither at 0 degrees or at 45 degrees or at any other angle. So that's how that is. And for a foundation like the one I just showed you, so a foundation subjected to a combination of V and H and eccentricity, well, there's quite a big difference between the two types of interfaces. I called it sigma greater than 0. That's sort of this kind of, say, questionable interface, and then sigma 3 greater than 0. That is the correct interface. And so you can see for small eccentricities, it's pretty much the same. 0, E on B equal to 0.1. It's not too different either, but as the eccentricity grows and the liftoff kind of starts to happen, well, then there's quite a big difference. The correct tension cutoff gives these sort of circular envelopes where basically the implication is that you have no horizontal strength unless you have some vertical force. Whereas the other questionable interface, well, it runs up like this, so you have the full horizontal capacity regardless of what the vertical force is. So there's a difference there. Different codes I can see make sort of different assumptions, I think, in this regard with the interfaces. This is the DNV code, which is very much in line with what I would consider the questionable interface. And you have also a Meyerhoff's very old solutions that actually, at least qualitatively, agree very well with this correct interface model, where you have these semicircles or something similar to it going down here to 0,0. And other codes have something in between. But so because we've had questions with this that people can sometimes not reproduce the results of other programs with GX, and when there's sort of interfaces and large eccentricities in play. And part of the, I think, reason is that the way interfaces are modeled in different programs. So this is how we model them here. Now to 3D, and 3D is kind of supposed to be the same as 2D. That's one of the ideas with GX. So there's two ways you need to be in a 3D world, and then you need to have the soil domain that's no longer a rectangle, it's kind of a box. You draw like that. And then there's two ways of modeling foundations as well. That's you can have a kind of a surface foundation, so a plate like that, and then you would apply the soil, let's say whatever this one, and then to model the foundation you would use typically a rigid plate. And this one here, even though you can't really see it, I think if I make it transparent, yeah, you can see there is an interface here. So it works exactly the same way as in 2D. Alternatively, you can do also an actual foundation, a block. Yeah, let me just delete this here as well. Oh, and that disappeared as well. Oh, okay. Should have maybe done like this and this. A block, so another box. Oh, that was my mistake. And like that, and then you can have the height is usually positive, but you can also have a negative height. So you extrude this box into the ground and then apply a not a rigid plate, but a rigid solid. And if we just make it transparent, then you can see there is the box. And with respect to loads, the same kind of ideas as in 2D apply. In 3D, we would often like to apply actual point loads in kilonewtons. That can't be applied to solids. That can only be applied to plates. So you can place a rigid plate on top of the rigid foundation that doesn't do anything to the physics, but it allows you to basically place point loads on the foundation like this, which I think is a lot more convenient than surface loads. So that's how to do that, and I have an example as well that I did some calculations. Here, first of all, just these are, this is a purely vertical loading, so multiplier loads, they're 0.25 each. So we have a total multiplier load of 1 or -1, and then we run the load multiplier analysis and get a solution that looks like this. And usually with the mesh, it doesn't look very impressive in 3D because most of the elements are underground. But if we just sort of do something like that, and then we can actually slice through the model. That's this tool up here where you can slice through the model and get a better impression of how it looks. And looks kind of similar to 2D, but not possibly exactly the same. It's there is of course a 3D effect, and the bearing capacity is also different. The shape factor for this is again an undrained analysis. So the shape factor, I think, according to the code, Eurocode, is 1.2, and it's about that we have as well. Effectively, if you compare 2D with 3D, I think 1.17. But so 3D foundations work kind of, it's analogous to 2D, of course, as usual. Setting up the problems is somewhat a little bit more difficult, and also running the analysis takes more time, but it is the way it is. And then also one with basically a moment. So here I have fixed loads equal to 25 at each of the corners. So a full a vertical load, a total vertical load of 100 kilonewtons, and then I apply a moment, and I do that by applying multiplier loads at these two sides, downward directed. And let me just turn on transparency. You can see over here at the other two corners, you have multiplier loads equal and opposite magnitude to basically give a moment equal to 1. And so the load multiplier analysis is aimed at determining the ultimate magnitude of this moment given a vertical load of 100 kilonewton. And that then looks like this, and you can see there is a good amount of lift off here as well. And so the tension cutoffs, kind of the interfaces with tension cutoffs kind of work, it seems. So that was bearing capacity. At least I have a few comments on these VH diagrams in the end as well. But settlements is also something that needs to be considered, of course. And there are different models that would be relevant for settlement analysis depending on exactly what kind of material you're dealing with. So I talked about cam clay last time with consolidation. That would be a relevant model. And otherwise, if it's sort of sand-like materials and you have you have drain conditions, then the recommended model is the hardening soil small strain model that we have now implemented. So this is a somewhat complex model, contains quite a few more parameters than Mohr-Coulomb, but the idea is it should also be more accurate. So the main sort of thing is that you have different stiffnesses in unloading, in loading and unloading. Mohr-Coulomb, you have only a single stiffness. As a Mohr-Coulomb is linear elastic, perfectly plastic. Hardening soil small strain, first of all, you have a variable stiffness, and then there's also a distinction between the stiffness in loading and unloading. That's not really so important if you just have monotonic loading. But nevertheless, so the important thing is kind of the non-linearity of the stiffness as you increase the load, starting from a very large potentially stiffness, E0, and then going up to, or at 50%, the E50, sort of the secant modulus corresponding to half of the ultimate load. And small strain stiffness is something that is sometimes is important, sometimes it's often is not really that important, but soils at very low levels of strain have a much higher stiffness than under sort of, let's say, normal levels of strain. The idea being that under very low levels of strain, it's first and foremost the grain-to-grain contact that governs the stiffness, and the grains, sand grains, say, are very stiff, much stiffer than an assembly of sand grains subjected to larger strains where the stiffness is affected by also the rearrangement of the grains. So this shows the shear modulus, which sort of versus the shear strain for kind of a traction type test, which kind of decreases like that. So a very large stiffness at small strains, very small strains, and then it gradually decreases to basically to zero, of course, at the ultimate limit state. So that's included in this model as well. But I think the main effect, what really makes it different from Mohr-Coulomb is the nonlinearity of the stress strain curve, and also the moduli that enter into the equation as input. So say E50 is also in itself stress dependent. So it follows this formula here where alpha here is supposed to be, they all follow the same kind of rule. But let's say it was E50. So we have a reference E50 at a reference pressure, and that reference pressure in OPTUM and everywhere else is 100 kPa. And then we have sigma 3 divided by that Pref to some exponent, which for sand is about 1/2 or a little bit more, 0.7. So that if we have a very large sigma 3, well, then we have effectively a larger elastic or E50 modulus, whereas if the sigma 3 is small, well, then the modulus also reduces as compared to the reference modulus. So it's not so easy to say exactly, is it 20 kPa, is it or MPa, is it 30, is it 50, what is it? It's the reference modulus, yes, but what it actually is in the course of loading up a foundation, well, it changes. as the stress level changes, as sigma 3 changes. And I did an example. It's a very simple example, but it's sort of just to illustrate. So it is an example of a strip foundation. And in this case, we run a so-called load deformation analysis. So pick that over here. And the load deformation analysis is a analysis where you basically increment this multiplier load in a certain way. There's different strategies for doing it. The default one is where you have a target displacement, and that displacement is the displacement at this result point here. So you go to 0.2 meters. Here, this is 2 meters wide. So it's 10% of the width. And you do that in a number of steps. And then the step variation may be constant. So you go with constant steps, or linear, meaning that you gradually increase the load step as you step up. So you start with something relatively small, and then you gradually step up in the course of 10 steps to reach a target displacement of 2 meters. So there's 3 models here. First of all, the hardening soil model. I've set E50 to 30. EUR, the unloading, reloading, 100. E0 is 250. Yeah, well, there's various other settings. We will have as well in the new year a webinar on some of the more complex models, including this one here. I don't really have time to go through all of it today, but just for the purpose of this, the question was how well does what do we get here with an E50 ref of 30 MPa, EU unloading reloading of 100, and then this 250 compared to more Coulomb. And a new feature we have just included in OPTUM, for those of you who are not aware of it, is this XY plotter, where you can generate XY plots, so including load displacement diagrams. So you start that up, and then you have the model here, the MC30. So that's a more Coulomb with 30 MPa, equal to the E50 ref for the hardening soil, and then one with 100 equal to the unloading, reloading reference modulus. So to see how do these different models compare. So MC30 first. So that's a more Coulomb with 30 MPa, and then 100. So that gets quite a lot stiffer. And then the hardening soil, which is actually very close to the more Coulomb with the Young's modulus equal to the reference E50. Maybe a bit of a coincidence in this case, but the dimensions and so on, the parameters are quite typical, so maybe not even that atypical. It's a little bit difficult, I said, to compare, because the stiffness of the hardening soil model depends on the stress level, and the stress level changes. So that's E50 here, or sigma 3. It changes as you step up from something relatively small to something much larger. So the soil gets stiffer as you approach failure, but there's also the effect that you get closer to the failure mechanism, so there's some decrease in stiffness. So it's a combination of different factors that all in all, in this case, lead to actually more Coulomb with a stiffness equal to E50 ref. Turns out to be really pretty much spot on. But that's the way a load deformation analysis is conducted. You set the relevant analysis type, then you need a result point, and then you need, of course, to specify your target displacement, the number of steps you want to run as well. And then this one, it's the default is constant, but it should really be linear. You pretty much always want to have smaller steps to start with and then larger ones as you get further up on the load settlement curve. Last thing is VH diagrams, and that's something that can be quite useful. So the setup could be something as shown here. This is an example. We wrote a note not so long ago. We'll distribute that. Isabella has promised to send it out with the mail that she sends out after the webinar with how to generate these VH diagrams. So if the example is in the note is for a skirted foundation subjected to a combination of V and H. And you would expect a VH diagram, so a VH envelope that would look something like this. And how to generate these diagrams, well, then Python scripting is really extremely useful. So you set up a script that basically applies loads in different directions. So applies a combination of V and H. So there's a V and H here, and then you can go around in an angle here and to basically cover the whole envelope. Except for typical VH diagrams, if you do that just with sort of a constant angle, then you tend to have a fairly unequal spacing of the points. So you can sort of move it into a scaled space, you could say, and then do it in a sort of a more efficient way. That's what is fully described in the note. So you need to first determine the minimum and maximum V and the maximum H, and then you apply. Also, you shoot out like this, but in a sort of a scale kind of way to get a more even distribution of the points on this note, on this VH diagram. And there's an example. This is from the note, and it looks, in this case, with the parameters that I have picked, it's a clay with some tension cut off here at the skirts, a clay where the underend shear strength increases with depth, and you get VH diagrams that sort of look, or a VH diagram in this case that looks like this. And depending on where you are on the diagram, well, you get one failure or another. There's sort of an normality rule that governs the relation between the horizontal and vertical displacement, so that if you're right down here, maximum vertical and no horizontal, well, it just sort of moves straight down. And as you move further up, well, you have the evolution of the mechanism in this kind of way, B, C, and finally D here, where it pretty much tends to come out of the ground. So there was an example for 2D and one for 3D, and in 3D it's sort of much the same. And finally, also with respect to moment, so you really kind of like a VHM diagram, a vertical, horizontal, and moment diagram. I think an easier way to think of it is in terms of an eccentricity, because then the procedure for a standard central VH diagram applies without any real modification, and you get these sort of VH diagrams for different eccentricities. You can, of course, convert this to a 3D VHM kind of, not a sphere, but something similar to maybe a rugby ball or something like that in this case. But this gives you as well the information that you sort of need. So I will send that out, that note, or Isabella will send that note out. It's a short note that sort of describes how to do it, and it also comes with the Python script for how to do it in both 2D and 3D. Okay, I think that's it for now, and I can see there's some questions, so let's move to those.